Hey guys, we're going to be going over how to analyze graphs of rational functions. Guys, I want to take a look at this graph here. This is your parent function. Take a minute to graph the function 1 over x, y equals 1 over x. When you look at that graph, you're going to notice that acts weird around some certain spots. If you take that and you drag it around here, you bring it closer to 0. Notice it wants to shoot straight up. As it approaches the y-axis, it tends to go up here from the right side. And if you're going at it from the left side, it tends to shoot straight down. Also, you're going to notice that it approaches the x-axis as you go to the right, and the same thing as you go to the left. So these functions behave this way for a couple different reasons, but mainly due to the fact that you are not able to divide by 0. I mean, that's really what it comes down to. I can't plug in 0 into that and get anything. It says undefined. So the graph wants to act really weird around 0. And if you move the graph around, you shift it left, right, up, or down, multiply, and stretch it out, and do all sorts of things to it. You can only make it even more complicated, add more spots where the graph wants to act weird around. So this lesson hopefully is going to make it a little bit more understandable as to why it acts that way. So let's dig in to some of the examples. First thing I want you to do is recall what happens when we look at a rational function like this. You've been asked in the past simply to define what the restrictions of a rational function. And a restriction for a rational function is any value that makes the denominator equal to 0, because you can't divide by 0, right? So if I try to say, well, what's going to make this 0? If I say x cannot be equal to 0, then that would be one restriction, because if I plug in 0 here and I multiply 0 by everything in here, you're going to get a denominator of 0. That's a restriction. Another restriction, well, what's going to make this equal to 0? Well, 3 minus 3 is equal to 0, so x cannot equal positive 3. And if that were x plus 3, x would not be able to equal negative 3. And finally, we have 3x plus 1. What's going to make this equal to 0? Well, you might not know right off the top of your head, but you can take the equation 3x plus 1 and solve that for 0. So if you take away negative 1, or if you take away 1, you get negative 1. And if you take x and divide by 3, and divide the negative 1 by 3, you're going to get x cannot equal 1/3. So that's going to be a restriction. You got 3 restrictions here: 0, 3, and negative 1/3. All of those values will make your denominator equal to 0. Because you cannot divide by 0, those are considered domain restrictions. So if you talk about domain, remember your restrictions were x cannot equal 0, x cannot equal 3, and x cannot equal negative 1/3. Let me write that down here for a minute. X cannot equal the following numbers: 0, 3, and negative 1/3. So as far as your domain goes, you'd want to say basically every number you can plug in except those values. So just in words, you would say all real numbers, except, and I would list them from smallest to largest. So, negative 1/3 is my smallest, followed by 0, and finally 3. That's my domain. We want to write this in interval notation. So you want to think about this like a number line. Think of the x-axis and imagine we put an open circle at those values. So we have negative 1/3. I'll say 0 is maybe right here. We got 1, 2, 3, negative 1, negative 2. Just jot those here. Your domain is everything except for those numbers. So if I look at 0, I'm going to put an open circle there. If I look at 3, I'm going to put an open circle there, and I can graph above 3. And if I look at negative 1/3, that's about right there, right? Negative 1/3. Your domain is going to be everything but that. So if I highlight on my number line everything to the left, that's going to keep going to the left from negative 1/3. The stuff in between negative 1/3 and 0 is good. The stuff in between 0 and 3, that's good. And then everything above 3, including everything to the right, those are all valid parts of your domain. So in interval notation, we're going to say something like this. On the left side, since that's negative infinity, we're going to say negative infinity up until my smallest number, which is negative 1/3. Since we can't include negative 1/3, use parentheses. Then we're going to put a u, that just means and. And then we're going to do our next interval. Negative 1/3 is 0. Followed by another u. 0 to 3 is going to be your next one. And then finally, we have the right side, which is everything above 3. So we'd say 3 to infinity. Remember, everything on the right side of the number line is infinity. Everything on the left side is negative infinity. So that's how you're going to want to write your domain for these problems. And again, this right here that I'm boxing in means the same thing as all real numbers except negative 1/3, 0, and 3. That's your domain. So let's talk about points of discontinuity. Points of discontinuity. To really understand what it means to be a point of discontinuity, you really want to look at the graph. So here I have graphed this function I called y f of x. And what I want to do here is I want to look around, and I made a little table, see all the values here. Notice that, I can pretty much get any value in this function, but there are certain ones that I'm not allowed to get, all right? Notice that my graph, remembering that negative 1/3 is negative 0.333 repeating. As I move my cursor up here, you're going to see that it doesn't want to touch negative 0.333 repeating. It does everything in its power to just shoot straight up and avoid that number. Well, I wouldn't be able to drag my point over it because it doesn't exist in the graph, because my graph says negative 1/3 is undefined. So that is a point of discontinuity. X is equal to negative 1/3. The same thing as your restriction, okay? And then once I pop up a little bit to the right here, you're going to also notice that my graph doesn't want to touch the number 0. All right, let me see if I can go up a little further. No matter how much I try, my graph does not want to hit 0, okay? 0 also is another point of discontinuity. That's the same as your restriction. In fact, there's a little piece of this graph way down here. And the graph is trying to get all the values between negative 1/3 and 0. If you drag through here, you'll see some of those x values. But it's not touching negative 1/3, and it's not touching 0. So those are both points of discontinuity. Now, if I keep dragging over here, it's going to appear that the graph does cross over where x is 3. But if I hover over it, there it is, you're going to see that it has this open circle right at 3, and it says undefined. The graph also will not touch the point x equals 3. So that's another point of discontinuity. So all three of those points, whether the graph's avoiding it at all or whether there's just a big hole in the graph, are considered points of discontinuity. So we're going to say the points of discontinuity are the same as your restrictions. So they're the same as your restrictions. They're the x values that the graph will not touch. We simply say x equals negative 1/3, x equals 0, x equals 3. So you're going to be asked to define if these points of discontinuity are removable versus non-removable. Now, the removable comes from, what you're able to cancel out. So if you remember, from our previous lesson about simplifying, if you have a factor on the top and the bottom, those would cancel out, right? Now, the point there, that restriction for that factor that we canceled out is x equals 3. So the one that you remove, cancel, let me write here, cancel. Cancel, that's a terrible way to write that, but the cancel, the restriction that you canceled, that's the removable one, okay? That's your removable one. So the non-removable ones, those are the ones that did not cancel out. So you notice that 3 canceled out. X equals 3 is one of your restrictions. It's the point of discontinuity. These two, no dice, all right? You don't have a way to cancel those out because there's no x on top. There's no 3x plus 1 on top. So your non-removable points are going to be the restrictions left over from, canceling stuff out. So you would say x equals 0 and x equals -1/3. They're all points of discontinuity, but the non-removable ones did not cancel after being factored and simplified. Let's move on to the examples. Example 1 on your handout is going to ask you to identify the restrictions, state the domain, and the removable and non-removable points of discontinuity. If you think you know it based off of my little introduction here, pause the video, try it on your own. Now, in some situations, you're going to need to factor sometimes the denominator, sometimes the numerator, sometimes both. In this case here, we need to factor the denominator to be able to see if we can cancel anything out and find our restrictions. So I'm going to factor x cubed minus 36. We have a GCF. Can you think about what that GCF is? If you think about x cubed minus 36x, you might recognize that they both have an x in them. So I'm going to pull out the x out of that set of terms. And inside I'm going to have x squared, because I'm taking one of the x's out, minus 36, because I took that x out there. Now I have it partially factored, but you're going to recognize now here we have a difference of squares. X squared minus 36 is a difference of squares. And so that's going to actually be parentheses x plus 6 and x minus 6. So we want to factor this expression. Now I want to rewrite this, so give me a second here. It's going to be x plus 4, x minus 6, divided by, my denominator is going to be x plus 6, x minus 6. I'm going to rewrite it so that my factors are written instead of my overall expression. Once you have it in that form, you're able to come up with some of the things we can cancel out, and as well as identify your restrictions. So as far as identifying restrictions, let's see if we can identify those. X cannot here be equal to 0. Here, x cannot be -6. And here, x cannot equal +6. Those are my 3 restrictions. So my domain is going to be all real numbers except for those 3 values. And there you have it. We're going to rewrite that in interval notation. Pause to see if you can write it in interval notation correctly. In blue, you see my interval notation. Remember, I'm going smallest to largest, so -6 is the first number in my interval, followed by 0, 6, and finally ending with infinity, starting with -infinity. Now let's talk about the removable versus non-removable points. We're gonna first see what cancels out. So if I'm looking at my canceled stuff, right? I'm gonna look at, well, I don't have an x plus 4, but I do have an x minus 6. Those cancel out. So that 6 right here, the +6, that would be the removable point because I canceled that factor out. So my removable point would be, or my removable point of discontinuity would be x equals 6. X equals 6. So that means the leftover ones are going to be those two, x equals 0 and x equals -6. Those are my non-removable ones because I did not cancel them out. They didn't factor, cancel. And that's how you interpret all those points of discontinuity, restrictions, and domain. Let's go on to example 2. To further expand upon our points of discontinuity, we have a couple names for those. There are 2 types of discontinuities in a rational function, rational graph function. One is going to be a vertical asymptote. So a quick thing, an asymptote in a graph is any line where imaginary line where the graph seems to not want to approach it. So if I have a graph like this, right? You've seen some graphs, and you might notice, well, hey, the graph is trying to touch this imaginary vertical line or this imaginary horizontal line here, but it's not quite going to reach it, and it doesn't look like it's ever going to go over it or touch it. Those are called asymptotes. They're imaginary lines the graph never touches. And we have a couple of things about vertical asymptotes in particular that are going to be useful in talking about our discontinuities. First of all, a vertical asymptote is always going to be of the form x equals some number. And take a look at the graph here so you can understand why. If I throw in, x equals 0, right? You're going to see this vertical line. And if I move that to the right or left, x equals 3, x equals 4. All it is a straight up and down line. Now take a look at your last graph here. Put that in Desmos. All right, take a moment to do that, please. In fact, pause the video and graph it, and then resume it afterward. So we're going to revisit our example 1, where it says x plus 4, x minus 6, x cubed minus 36x. Now remember, we had already factored it and got our discontinuities. So we should know that our removable point of discontinuity from our previous graph, let me look over here, was 6, and our non-removable ones were 0 and -6. Now if I graph that, you're going to notice a couple things. First, if you take a look at where x is 0, so x equals 0 would be something the graph seems to want to approach here, but doesn't quite touch. All right, if you drag that over here, x will never quite be 0. Same thing over here. Okay. It also doesn't want to touch. Can you think of the other value it doesn't want to touch over here? Look at the value of x, -5.973, versus over here, -6.025. There seems to be one number right in the middle of those that it seems to want to avoid. And if you guess -6, you're right. Both 0 and -6 are considered vertical asymptotes of this graph. Now, the other discontinuity was, I believe, 3. Or not 3, I think it was 6, wasn't it? Yeah, so let me put that over there. Now the graph seems to hit 6, but if I scroll over this, you're going to notice that 6 says undefined. Okay, there's a big open circle right there at 6. So that's a point of discontinuity too, right? So let's kind of analyze in the context of this graph what's going on with that. Okay, remember that let me go ahead and factor this real quick. This was x plus 6, and x minus 6. Okay, and remember that we had canceled these out, and so our removable point of discontinuity was x equals 6. And our non-removable, we had 2. Non-removable, we had x equals 0 and x equals -6. Well, it turns out that the removable point, that's what we call a hole in the graph. Okay. That's where on the graph there's just a big open circle that doesn't really exist when you plug in 6. The non-removable points, these are called vertical asymptotes. Vertical asymptote. Funny name, but that's what they're called. And they're always going to be where the ones that do not cancel out. So 6 was a hole in the graph, and 0 and -6, vertical asymptotes. And I should say x equals 0, x equals -6 would be those. X equals 6 is your hole in the graph. So your vertical asymptotes are your non-removable points of discontinuity, and your hole in the graph is simply the one that gets removed. All right, let's go into example 2. After going through it, explaining vertical asymptotes and hole in the graph, if you feel confident, see if you can find these on your own, pause this video right here and try to see if you can factor, cancel, and find the vertical asymptotes and hole in the graph. I will wait. Not really, but if you pause the video and you unpause it, then it will have been weighted for you. All right, I got this thing factored on the denominator to x, x plus 3, x minus 3. You'll notice there's a GCF first you can take out. Then we have a difference of squares again. So x plus 3, x minus 3 will give you x squared minus 9. And then if you go over here, you're going to notice that we have a pair of factors on the top and bottom, x plus 3, that cancel out. So based off of your values down here for all your points of discontinuity, you have 0, -3, and 3. A couple of them are going to be vertical asymptotes, and one of them is going to be in the hole in the graph. Have you figured out which one? Well, let's check. So the vertical asymptotes are going to be your non-removable. And what did I not cancel out? That's right, x equals 0 and x equals 3. Those are your vertical asymptotes. Vertical asymptotes. Straight lines, imaginary lines that the graph tries to avoid at all cost. The hole in the graph is the removable one. So the removable one is your hole in the graph. That's just going to be x equals -3. Graph it if you want. Oh, look, here it is. Take the time to do that for yourself. So if you remember our vertical asymptote, we had 2 of them, x equals 0. Huh. Well, that graph does not want to touch 0. Look at that. Look at that graph, like just approaches it, but never touches it. There's another one, x equals 3. Look at the graph, doesn't want to touch that one either. It's avoiding it at all costs. And we have this hidden one here, this hole in the graph. Let's see if we can find it. There it is. Big open, well, it's not that big. Open circle. Oh, lost it. There it is. Undefined hole in the graph. Still a point of discontinuity, but because it canceled out, it doesn't look like it is. Make sense? All right, guys. Let's go to the next example. Did you know that graphs can have horizontal asymptotes too? They're actually a little bit easier to find because there's a couple rules we can follow. Horizontal asymptotes, of course, are like this, and they're always going to be of the form of y equals a number. Remember, horizontal asymptotes, y equals a number because that's a flat line, and a flat line is going to be horizontal. Graphs have sometimes horizontal asymptotes, and sometimes they don't. Let's analyze to see what they are and how to figure that out. So we have a few rules to follow when it comes to horizontal asymptotes. It makes more sense when you see them graphed, but let's examine the first rule right here. All right, when you have a smaller degree on top, such like this one, 2x minus 12, the degree here is 1, and a larger degree on the bottom, so in this case here, you're going to be a third power degree, those are always going to have horizontal asymptotes that are actually just the x-axis. So it's just going to be y equals 0. Y equals 0 is actually the x-axis. So I'm going to go ahead and write that. Here, I'll show you. Graph that so you can see it. All right, here's the graph of that. Now, if I graph 2x minus 12 over x cubed minus 36x, it's got some vertical asymptotes, but I'm worried about the horizontal right now. Now, if you do y equals 0, you're going to see that that flat line's basically to the x-axis. And anytime where you have a smaller number here on top of a larger power on the denominator, that'll always be the case. So even if I put a 2 there, it's still going to flat line to the x-axis. Now, if I make that a 3, that's going to be a different story. But anytime it's going to be smaller than the degree on the bottom, the large degree on top is smaller than the degree on the bottom, it'll always be y equals 0. Y equals 0. All right, next rule. Rule number 2. If you have it flipped where the higher degree is on the top than the bottom, turns out there is no horizontal asymptote. Let's graph that. So when you have a higher exponent as your very highest exponent on the numerator, then the graph is going to want to act differently. It's going to want to act like diagonally or in a parabola or some form, but it's not going to want a flat line, okay? So you simply say, in this case, no horizontal asymptote. Let's examine the next one. Now, if it turns out they have the same degree, so in this case here, we have a third power divided by a third power, then it turns out the horizontal asymptote is just going to be y equals whatever your lead coefficients divide to. So if you look at your lead coefficients, notice that they're 2 over 4. Now, if I look at 2 over 4, I know that 2 over 4 is equal to 1/2. That's 0.5. So y is going to be equal to 1/2. That would be your horizontal asymptote. So, if this were like 3/5, it would be 3/5. If it were -8/3, that's what it would be. So whatever your lead coefficients divide out, that is going to be y equals that number for your horizontal asymptote. Let's graph it. Okay, guys, here's the graph of this function that I have on that third part of the table. Now the graph, if you notice there, it's not flatlining at the x-axis anymore, okay? So it looks like it's shifted up a little bit. And we can verify that these two numbers, 2 over 4, is going to be indeed the line that the graph strives to touch, but it never quite touches. If you zoom in here, it's never going to be this be 2/4 or 1/2, but it's going to be really close, right? The graph wants to touch 2/4. It just doesn't have it in it to complete the task. So 2/4, of course, is going to be 1/2. So same deal, just a reduced version of that fraction. All right. So now that you have those 3 rules in your toolbox, identify the horizontal asymptotes for these 3 functions here. We got x squared minus 3x over x cubed plus 5, 2x plus 4 over 3x plus 2, and x to the 5th minus 1 over x cubed plus 7. Pause it, try it on your own. Use these rules to help you. Unpause it, and you can check with me. Welcome back, guys. So let's go ahead and see if we can check those using the rules alone. If you want, you can regraph it and check the asymptotes that way. I'm going to save time on this video and not graph for you. Let's start with letter A. So we have our degrees 2 and 3. Now, if you look at that, this is going to be a lower degree, and this is going to be a higher. So if I use my rules, if I go to my lower over higher, smaller over larger, then that's going to tell me my horizontal asymptote is simply going to be y equals 0. So you can verify that. Part B, if you look at my x's and I only have an x, well, that's a degree 1, right? They have the same degree for both of those. So if you look at the coefficients for that, that's going to be your horizontal asymptote, y equals 2/3. And then my last one, you notice this is going to be higher, right? And anytime this one is going to be higher on top, it's not going to have one. So we'd say none. And so asymptotes on the horizontal side are actually not required to graph it, because you can use that set of rules to get them pretty easily. I'm going to conclude this video here. The next video is going to go over example 4 and 5. Follow that one so you can understand how to actually complete the whole thing together. We're going to put it all together and be able to write a function based off the graph alone. Thank you for watching.